Are you in quantum space or are you in physical space? Physical space is three-dimensional. Quantum space can be two-dimensional, can be infinite dimensional. Right now, we've got to make the transition into Hilbert space. And let's see how that goes. If we do it right, your intuition about quantum mechanics will be right, and mine will too. Let's see if this helps out. Classical state. Well, what's a classical state? Well, we got three dimensions, x, y, z for position. And if we have momentum, the forces that drive that position to do different things, those are at an x, y, and z. That's a three-dimensional vector quantity. So this really ends up being a six-dimensional space. And what's important is you can measure this as just as finely as you want to. So it's just a continuous space. You're only limited by the precision of your instruments. There's no quantization. Quantization, quantum. This quantum state, just to make it as simple as possible, this quantum state lives in a two-dimensional Hilbert space. And the state in green is made of the two basis dimensions. So you have one that's called a 0 basis vector and a 1 basis vector. How much simpler can it get? And I've got the 0 basis vector up here, the 1 basis vector there, and the two components of those basis vectors that make up this little green arrow. And I've tried to make sure that you see that this green arrow is kind of going to end up being like the length of one of these two arrows, this unit length, but it's going to have different components that will point it in different places. Now, you might say, well, gosh, that's easy. This is an easier picture than this one over here. Well, just wait. You can imagine it's not that easy, but let's hold on to that idea for now as we progress to the next stage. Okay, moving forward very slowly, notice some more things showed up on the board. One of those things is, it says the physical state equals a ray. Now, what in the heck is a ray? Well, let's see. Is this green arrow ray? Yeah, that's a ray. But I thought it was a vector. Well, the vector is determined by a length and a direction. A ray is, gosh, it's so much simpler. A ray is just the direction. So this, if I make this arrow longer, it's still the same ray. As long as it's pointing in a particular direction, then that determines the ray. And that ray can be represented by any number of vectors, any length, as long as they're pointing in the same direction. So that's really important. So whenever I say a ray or a physical state, you're going to know to point out what is the direction of that thing. So as you can see, these components up here can determine the ray. And here's the state. Look at that. Maybe I should have underlined the ray in green. Okay, just because we talked about a ray, I've kind of drawn these things a little bit differently. I've got these a little bit longer, so this phi is a ray and this psi is a ray. And I did something here where I introduced this thing called an inner product, where we take this bra vector and the ket vector. I haven't talked too much about those yet, but let's just go ahead and jump in and use them. If I take the inner product of the same state, then I just end up equaling 1. If it's not 1, then this inner product will tell us something about the probabilities between these two. A lot of times we have operators that don't change anything about the relationships. For instance, let's say that these things both rotated, but they rotated together. Then the relationships between these physical quantities would not change, and that would be called a unitary operator. Okay, we're about to wind this up. You might be happy about that. These two components, the alpha and the beta that we talked about, and of course there's a couple other components for this phi ray that's here, those are going to end up being complex numbers by necessity. So we'll have a two-dimensional complex plane that we're working with, which will make things a little more complicated in your head. The inner product will maintain the geometry, which will help us identify observables. Hey, observables, those are the things that we want to see. And this idea that we can maintain symmetry with certain operators. This is the new reality. This is the Hilbert reality. Now notice that it's not physical space. It defines everything that's going to be happening in the reality of quantum physics. So as long as you live in the macro world, you're in good shape. Don't worry about this. If you want to learn about quantum chemistry, though, this is your new reality.